University system requirements and suitable database architecture. System requirements analysis. Data to be managed, students, faculty, departments, courses, enrollments, examinations, results, and all. Functional requirements, student admission and registrations, course enrollment and allocation, timetable management, examination, result processing, fee collection and accounts, then library book, issue return, reports and dashboards of for management. Data requirements, centralized storage for all academic and administrative data. Data consistency and integrity, secure access with role based permissions, backup and recovery. Non functional requirements, multi user concurrent access, high availability and reliability, scalability to support growing data users, performance and fast response. Data security and privacy, users, student, faculties, admin, staffs, librarian, accounts, department, and management. Proposed database architecture, three-tier client server architecture, data layer where the database server, university database will be stored, then the application layer, application server where the business logic exists, authentication, validation, processing, and reports, presentation layer, user interface, web or mobile or desktop. Users will be student, faculty, admin, and so on. Justification, centralized database ensures data consistency, integrity, and security. Three-tier architecture separates UI, business logic, and data for better maintenance and scalability. Supports multiple users concurrently from different locations, easy to backup, recover, and enforce access control. Scalable and new modules placement alumni can be added easily. Hence, a three-tier client server DBMS architecture is more suitable for the university system. A multinational enterprise intends to integrate distributed branches into a unified database system, evaluate different DBMS classifications, and recommend an appropriate model with justification. DBMS classification. DBMS can be classified on various bases. For multinational enterprise, the most relevant classifications are data model, hierarchical database, network database, relational database, object oriented database. Hierarchical data organized in a tree structure. It is not suitable for distributed branches. Data organized in a network graph structure, that is also not a good choice. Relational database, data in tables, relations, that is highly suitable for different distributed branches. Object oriented database, data as objects, medium. Number of users, single user DBMS, multi user DBMS, used by only one user at a time. This is not suitable for distributed branches. Supports concurrent access by many users. Yes. Number of sites, centralized DBMS, distributed DBMS. All data stored at one site, data stored at multiple sites connected by network. Data distribution. Homogeneous DBMS, heterogeneous DBMS. Same DBMS and data model at all sites. Different DBMS or data models at different sites. High. Then workload, OLTP DBMS, OLAP DBMS. For transaction oriented operation, for analytical and decision support, OLTP. A recommended model for distributed relational DBMS. Why? Because data is stored across multiple branch sites geographical distribution, and connected via network. The relational model provides simplicity, data integrity, and standardization (SQL), and supports the replication and fragmentation for high availability and fault tolerance. Enables local autonomy. Each branch can operate locally and global integration, unified view of data. Cost effective and widely supported by modern DBMS, Oracle, PostgreSQL, MySQL cluster. Conclusion: the distributed relational DBMS is the most suitable model for integrating distributed branches into a unified database system because it ensures data consistency, reliability, scalability, and ease of management. Here is a startup which aims to develop a scalable e commerce platform with high concurrency handling technique. Then design a conceptual database schema and justify how three schema architecture and data independence support scalability and maintenance. Conceptual database schema. ER diagram. Customer places the order which contains order items, refers to product, order payment, customer has address, order pays payment. In this manner, we have three schema architecture. Three schema architecture diagram. This first one is internal schema, conceptual schema, and external schema. The first thing is there will be the stored database. After that, you will have internal level, that is physical level. Internal level is the physical level, conceptual level, logical level, external level, view level. Internal schema, physical storage, tables, indexes, files, partitions. Conceptual schema, overall logical structure of e-commerce database. Then the external level contains customer view, admin view, inventory view, analytics view, like this. Then we have the entities and the key attributes of this. Customer ID, name, email, phone, address ID, address of address ID, street, city, state, pin code, order ID, order rate, total amount, customer ID, order item ID, order ID, product ID, quantity, unit price, discount, product ID, product name, category ID, price, stock, category ID, name and all, payment ID. Then how it supports the scalability and maintenance. Data independence. There are two types of data independence: logical data independence, physical data independence. Logical data independence is changes made in the conceptual schema, for example, adding new attributes, do not affect the external views and applications. That is, changes made in the conceptual schema that do not affect the external views and applications. Physical data independence means changes made in the storage structure. Changes made in the storage structure do not affect the conceptual or external schema. For example, adding partitioning, indexing. Changes made in the storage structure do not affect the conceptual or external schemas. Scalability. Multiple views allows different applications, web, mobile, admin, analytics to access only required data. Data can be horizontally partitioned across servers without changing the conceptual schema. Supports load balancing and high concurrency. Maintenance, centralized conceptual schema ensures consistency and reduce redundancy. Easier to modify internal storage for performance without affecting user applications. New views and or applications can be added without impacting the existing ones. Conclusion: the proposed schema efficiently manages e-commerce data using three schema architecture ensures data independence, which improves scalability, flexibility, security, and simplifies maintenance of the system. Consider the following relations. There is hotel, hotel number, name, address, room, room number, hotel number, type, price, booking, guest, booking, room, and hotel. List the names and addresses of all guests booked the hotel, which is located in Chandigarh, alphabetically ordered by name. Select the all the guest name and their guest addresses we need. So select g dot name comma g dot address from guest G and booking B comma hotel in which the G dot guest number equals to B dot guest number, B dot hotel number equals to H dot hotel number, H dot and H dot address equals to Chandigarh. Order by G dot name. Order by alphabetical order. So order by G dot name. List all the family's rooms with a price below 400 per night in ascending order of price in Hotel RVH. It's all family rooms. We just have to select the room number, type, price from room where hotel number is equal to select hotel number from hotel where hotel name equals to RVH and type equals to family and price is less than 400 order by price ascending order. How many hotels are there? Select count star as number of hotels from hotel. Number of bookings per hotel more than 3 booking. Select H dot hotel number H dot name count of star as number of bookings from hotel H and booking B where H dot hotel number equals to B dot hotel number. Group by H dot hotel number comma H dot name. Group by having count of star is greater than 3. Group by H dot hotel number and hotel name. List guests ordered by name and address. Select name comma address from guest order by name address. Find guest where name ends with N. Select star from guest where name like percentage N whose name starts with S percentage. Then we have like S means starts with ends with N. Consider the following schema. This is employee database. In EMP, SSN, name, address, salary, super SSN, that is the supervisor's SSN, and all are there. Add a column job with the domain to the employee table. Alter table EMP, add job varchar of 20. Insert a records into EMP project and work on. Insert into EMP of SSN name, address, salary, super assistant, comma, dino, job, values, the same thing. Then insert into project of pno, pname, plook, and dn, values of same thing. Then update the column salary with the new value. Update emp set salary equals to 60,000 where SSN equals to 101. Rename the column of employee table ADDR as address using alter command. Alter table emp, rename column ADDR to address. We will use the rename command itself. Rename column ADDR to address. Delete the employee whose SSN is 105. Delete from EMP where SSN equals to 105. Count number of employees' names from employee table. Select count of name as number of employees from EMP. Find the maximum age of from employee table. Select max of age as max age from EMP. Select min of age as min age from EMP. Find the salaries of employees in ascending order. Select a salary from EMP, order by salary in ascending order. Find group salaries of employees. Select salary. Select salary, comma, count of star as number of employees from EMP. Group by salary. Retrieve the birth date and address of the employee whose name is John B. Smith. Select birth date, address from EMP where name equals to John B. Smith. To retrieve the data of employees who works for research department. Select e.name from EMPE, department D where e.dno equals to d.dno and d.dname equals to research. Find name, job and salary of all employees who get the minimum salary. Select name, job, salary from EMP where salary is equal to select min of salary from EMP. To retrieve the name of employees who works on the project that Kumar works, select e.name from EMPE works on W where e.ssn equals to w.ssn and w.pno equals to select w2 of pno w2.pno from emp e2 works on w2 where e2.name equals to Kumar and e2.ssn equals to w2.ssn. Select w2.pno from emp e2 works on w2 where e2.name equals to Kumar and e2.ssn equals to w2.ssn. To retrieve the manager's name with at least one dependent, select distinct e.name from empe dependent d where e.ssn equals to d.ssn. d.ssn. For each department, retrieve D name, number of employee, and average salary of the employees in that department. Select D dot name, count of E dot assistant as number of employees, AVG of E dot salary as average salary. From department D EMPE, where D dot dnum equals to E dot dno, group by D name. To retrieve the employees' names and their supervisor name, select E dot name as employee name, comma S dot name as supervisor name, where from EMPE left join EMPS on E dot super SSN equals to S dot SSN. Drop any one foreign key constraint on workflow table. Alter table works on drop constraint. FK works on EMP. Alter table works on.
ನೆಕ್ಸ್ಟ್ ವಿಡಿಯೋದಲ್ಲಿ ಮತ್ತೆ ಸಿಗೋಣ. ಅಲ್ಲಿವರೆಗೂ ಫಾಲೋ ಮಾಡಿ ಟೆಕ್ ಗರ್ಲ್ ಕನ್ನಡ.